There's no syllabus right now, so I'm going to distribute the syllabus by mail, as well as perhaps next time I'll give you a printout copy of the syllabus. This course will be an introductory but somewhat upper-level course in linear programming. Some of you might have been already exposed to linear programming concepts from your undergraduate courses. Let me see how many people have been exposed to, for example, introductory level linear programming models in a course such as 202 here. Okay. How many people have no idea what linear programming problems are all about? Just raise your hand. Which department are you from? EE? You have no idea what linear programming is all about? A little bit. Okay. Well, you'll have to bear with me. At the beginning, I'm going to give you somewhat more elementary models, but then later on we'll start talking about a bit more advanced models, not too advanced, but something a little bit more than undergraduate level. And then after that, I'm going to start talking about actually solution approaches to linear programming models, because this course covers basically the geometry as well as the algebra of linear programming problems, in addition to some initial expository material on formulations. And later on, we'll start going into somewhat more specialized topics. And so, if you're not familiar, you'll have to perhaps put a little bit extra time at the beginning compared to other people, okay? Anybody from management or economics here? Did you get exposed to some linear programming material before? In what course?
I took mathematical programming from IE department.
Which one? The one taught by Bahar Kara? Okay. So you have some familiarity. What about you?
I took management science from management department in undergrad.
Who taught it? I asked the wrong question. It's okay. Which are this management department here in this university? Okay. Anyway, for those of you who may not be too familiar with formulation examples, you'll just have to do some extra work at home to perhaps cover what we want to cover during the course. Now, the course syllabus, I don't have it with me. Nevertheless, I'm not going to give you any homeworks. That's one important component of the course. Last semester, I actually gave weekly homeworks, and then many people found it beneficial. Nevertheless, some people really complained about it. You know, this is too much work. Well, I don't really care. It's, you know, learning is your business. You learn. My business is to make it easier for you to learn the material. So if you attend the lectures, it's to your benefit, because I extract the more important stuff from the less important stuff. And so if you can learn, for example, maybe 80% of the course material in the lectures, you'll be really in good shape during the semester for the exams, etc. Okay? But if you miss classes, you'll have to make up for that, of course, using the book. In which case, come on in. In which case, you can certainly do it. Nevertheless, there are a lot of topics which may not be available in the book. The book is Bazara, Jarvis, and Sherali's book, the second edition from 1990, which is somewhat an old book compared to some of the more recent books available. Nevertheless, this book is quite a good one, in my judgment, both notation-wise as well as the way he puts the material, exposes the material. For that reason, the main material is based on that particular book. Nevertheless, there are many, especially geometrical ideas, which may not be available in that book, in which case you'll have to somewhat follow my arguments in the, on the board. Okay? I don't intend to use any PowerPoint presentations here because it typically seems to work against you. You get bored because you're too passive during PowerPoint presentations. For that reason, I make a habit of using the board just for you guys. Not for myself because I get tired actually just writing down a lot of stuff. Nevertheless, you can take your notes, etc. Now, even though there are no homework assignments, I am going to give you problems to work on. So you just do it on your own, maybe just individually or perhaps in teams of 2 or 3 people or whatever. If you want to come and discuss with me your solution approach, you can always drop in to my office, and if I'm available at that point, you can certainly discuss it with me. I prefer to have a walk-in policy. Don't send me email and try to make appointment. I just don't prefer that. The reason is, if I give you an appointment time for a mundane business such as discussing a homework, then something else comes along after I give you the appointment, and I have to cancel. I don't like canceling. Okay? Something else could be more important, such as a department meeting or whatever. For that reason, I don't wish to give you appointments. You just try your luck. You call me up. My extension is 1960. You call me up, and then you just say, can I come in for maybe discussing a particular homework problem? Fine, I say come in, so I'm there. If you call me up and I'm not there, I'm either out, perhaps just momentarily, maybe a few minutes, or perhaps out for 1 hour. I don't know. You try your luck again. But I do post office hours, which I forgot now. I think it's on Tuesdays from 10:30 until 12:30 or so, okay? Except for tomorrow, because tomorrow I have a dental appointment, so you can't see me tomorrow. Nevertheless, on Tuesdays, in the office hours, you can just walk in without having to call. Outside of office hours, it's good for you to place a call if you're outside the department. If you're in the department, just walk in and see if I'm there or not. All right. There will be 2 exams. One is a midterm. The other one is your final. The final will be comprehensive. Nevertheless, comprehensive in the sense that you cannot really learn the material in the latter part of the course without mastering the material in the first part until the first exam. So do master it. I do expect that. Have a good idea of what we're talking about. And the final exam questions are typically selected from the latter portion of the course after the first exam. Nevertheless, there may be some stuff that you may have to rely on from the beginners, from the beginning material. All right, each exam will contribute 50%. That's it. That's the way I grade, because there's no homework, okay? Now, if you guys feel tension about this and prefer to have some kind of a project or something of that nature, that's fine. I can think of that. However, project work is not easy. And whether or not you really need it, I don't think so, not for this course. If there's an advanced LP course, then of course we may also think of a project. So anyway, this is the logistics of this particular course. Do you have any questions on? Yes?
How will be the nature of your exams? Will we use like any kind of software or laptops? Or
no, you don't need any laptops or any kind of computing device during the exam. You just use your brain That's all I need. And of course, some computation by hand, manual computations. But the course is not just about computations, but also in some more foundational work. So the exams will be closed book, closed notes. I used to permit the use of books as well as notes, but then that does not seem to work to the benefit of your learning, so I decided not to. So do study and just come to the exam, just having no material on the side, okay? Just yourselves. Any other questions or comments? Okay. Any PhD students here? Okay. Well, this is going to be a typical master's level course. Nevertheless, it's not like an undergraduate course, so you should expect some rigor as well as mathematical maturity in approaching the course. Not at the beginning, but as things develop. Okay? All right. If you have no questions, I'm going to start the material at this point. Linear programming is initially conceived by George Dantzig. Back in 1947. He's an American of, I think his father, Tobias Dantzig, is a mathematician of Russian descent. Dantzig, he was at that time, well, he was born in 1914, so he was probably, how old? 33 or so at that time. During the Second World War II, during the World War II, operations research, which is sort of an esoteric name actually, which doesn't explain what it means all about, the British actually put together a team of scientists of from different disciplines called Blackett Circle, because the chair of the director of the group was a guy named Blackett. So Blackett worked with a multidisciplinary team of people to work on military operations. And then some of the techniques they developed, this was the beginning of the operations research as a discipline. And some of the techniques they actually started developing seemed to be quite useful after the war, and especially in the United States as well as in Britain and later on in Europe and the rest of the world. These techniques the people started working on these techniques in further elaboration to actually use them in the setting of business and managerial decisions, as well as manufacturing, industrial decisions, etc. Some of you are quite familiar with all this, or maybe you're not, I don't know. Nevertheless, linear programming is part of this myriad of different mathematical and computer-based techniques that came to being as operations research. Linear programming is at the very heart of that. Because once you start learning linear programming, later on you can start using it in nonlinear programming as well as in integer programming, which some of you have already been taking. Okay? Dantzig, he was employed at that time in the Air Force. And the Air Force was dealing with problems of managing their operations in a reasonable way within the limitations of so-called limited resources. Now, when we talk about limited resources, of course, we're talking about things such as money. You don't have infinite amount of money. You have a budget restriction. You have certain manpower restrictions sometimes. Sometimes you have material restrictions. These are all different kinds of resources. And when you have limitations on these resources, and if you have different activities for using these resources, these activities typically compete with one another for the use of these resources. And for that reason, you have to find a proper balanced combination of these activities which do not exceed the resource levels. So the Air Force was dealing with these kinds of activities. And George Danzig was assigned a project of this sort to look at such problems. And he was a hardworking and good-natured man, apparently. So he came up with what he called programming problems in linear structures. So that was the first name he put together. Programming problems, or programming in linear structures. Of course, this was kind of a long name. Later on, I forgot now, but someone suggested that, well, I think it was Koopmans, why don't we use just linear programming rather than using this long name? So anyway, after that, the term linear programming has been in quite frequent use. Danzig actually introduced what he called an objective function. There was no objective function. The concept of objective function was not really part of all these problems that he was working on. So he introduced this concept of minimizing or maximizing some kind of a linear function of some sort, subject to or provided that you meet all these restrictions given by the limited resources. Okay? And it turned out that prior to Danzig's formulation of linear programming problems, there was a guy called Kantorovich in Russia, and also Koopmans in the United States. These people were working on economical problems back in 1940s, prior to Danzig's work, maybe 1941-42. Kantorovich was working on input-output analysis in modeling the economy of some portion of the economy of Russia, and Koopmans was doing a similar work also in the United States in 1945. This one, he was working on these problems in 1941-42. And he did, in fact, publish a work in Russian in Doklady Sciences, but nobody knew about it. Koopmans did not know anything about it. And Koopmans also, he published some work. Later on, these two guys actually received the Nobel Prize back in, I think it was 1980s, 1987 or something. Don't quote me on the dates, but actually, of course, many people objected to the idea of Kantorovich and Koopmans having received the Nobel Prize, whereas many people who work in operations research and in linear programming thought that it was more just for George Danzig to have received the prize. Nevertheless, you know, once the prize is given, of course, you can't take it back, so that's the story. But the father of linear programming is George Danzig, for all practical purposes. Why? Well, because these two people, even though their contribution was quite valuable, it was just a formulation type of, or an approach type of situation. They formulated a particular type of economical problem in terms of input-output streams, and it turned out that all of the streams they had were expressible in linear programming terms, in terms of linear functions. There was no objective function in their analysis, whereas Danzig's main contribution is, first of all, he formulated the linear programming problem in a more general context for essentially anything. Number two, he devised a very particularly elegant and effective method for solving such problems. It's called the simplex method. The term simplex has really nothing to do with the actual method. Initially, it had to do with what we call simplices in geometry. Nevertheless, it's an algebraic method of efficient working. It's an iterative method, and it works fine. But he formalized all these ideas. It's the product of a single mind. He did a good job. In fact, his contributions have later on continued in a strong sense in duality as well as other aspects of linear programming, especially in solution aspects. And so he's a legendary figure. Don't forget the name, Danzig. It's an important figure. It should be in your head all the time for your life, I think, in my judgment, because he's a good man and he contributed a lot to this discipline. He passed away, unfortunately, back in 2005 at the age of 90. He was still working on different problems at that time. Good producer, good hard worker, and I hope many of you go after his example. Okay? All right, so that's sort of the story part of linear programming. So what I'm going to do is, before I give you the general structure, let's just begin with an example. Students like examples. So we'll just look at an example problem, get the main ideas, and then proceed from that point on. So for my example, let's call it example 1. Well, let me just write it here first. Let's suppose we have a car manufacturing plant, or an assembly plant, whatever you want to think of. And just for the sake of simplicity, let's just assume there are two types of cars produced in the plant. And one of them is sort of a luxurious type, so let's call it the Lux wagon. And I'll abbreviate it to LW. The second one is more for down-to-earth people, so it's called the Volkswagen. And I'll abbreviate that to FW. Now it turns out that per Volkswagen, you can sell it to people at a profit of, say, 20,000 Turkish liras, okay, per Volkswagen. Again, per Volkswagen, you can sell it at a profit of 10,000 Turkish liras per car. This is really a toy problem, so don't expect anything as well defined as this one when you work actually on real-world problems. Real-world problems, this is just a word of caution. Real-world problems, they come in obscure fashion. When someone presents to you a problem, normally it's not well defined. It's got many different pieces of information associated with the problem. It's your job, if you're an analyst, it's your job to extract the more essential information, delete the more unnecessary or less relevant information from the rest, and try to formulate or try to make some sense of the problem on your own. But here, all the information I give you is used in some way in the problem formulation. Nevertheless, life is not like that. So that's just a word of caution right now. So in this particular car manufacturer, let's assume that we've got 3 departments. assembly department for assembling the cars. Number 2, the painting and finishing department. Where you paint the main body. And finally, the checking out and testing. Okay? So, 3 different major departments. Now, in the assembly department, each Volkswagen requires 150 man-hours. So, Volkswagen requires 150 man-hours per Volkswagen, whereas the other one requires 60 man-hours per car. In the painting and finishing department, each Volkswagen requires 50 man-hours, and each Volkswagen requires 40 man-hours. And finally, in the checking out and testing division, each Volkswagen requires 10 man-hours per car, and each Volkswagen requires 20 man-hours per car. That's the type of information we've got. Okay? Now, per production run, which could be a weekly or monthly production, we've got 30,000 man-hours available in the assembly division. And 13,000 man-hours available in the painting and finishing department, and 6,000 man-hours available in the checking out and testing division. So, the main question is, how many of each car type should we be producing per production run to maximize the profit while, of course, obeying all these conditions imposed on us? Okay? How many Volkswagens and Volkswagens to produce per production run? To maximize the profit per production run while obeying the constraints on man-hours availability in the 3 departments. Okay. When you have a problem of this sort, before you attempt to formulate anything, it's good to organize yourself. So put some kind of a tabular structure of some sort, so things become sort of visible at a single glance. It helps you. In fact, many of the business people in the business world, that's what they try to do using all these Excel sheets. They generate so much data. Sometimes it's, well, actually, in most of the time, it's too much because you can't process all that data. And nevertheless, it's all organized. So in this case, if you want to organize your data, you can surely do it in the following way. Some people would like to do it in a different way. Nevertheless, this is my way of organizing. So I would take 3 columns for each of these different departments: assembly, painting and finishing, and then checking out and testing. And let's put down the first row for Volkswagen, the second row for Volkswagen. And let's just put down the information for consumed man-hours in each of the departments by each type of car. So Volkswagen, 150 man-hours in the assembly. So let's just put 150 man-hours here. And the other one, Volkswagen, you spent 60 man-hours per car in the assembly department. Similarly, in the painting and finishing department, you've got 50 and 40. And in the checking out and testing division, you've got 10 and 20. These are all man-hour type of units. Okay? Now, what's the profit level? Per Volkswagen, it's 20,000. So we have an extra column here, 20,000 Turkish liras. The other one is 10,000 Turkish liras. And you've got some availabilities in terms of man-hours in each of the departments. The available amount, we can just put it down as an extra row here. We've got 30,000 available in the assembly, 13,000 available in the painting and finishing department, and 6,000 in the checking out and testing division. Okay? It's compact, it's good. You know, you see things at a glance. Once we've got this, the next thing to formulate these things is to think of a good decision variable, or a good set of decision variables. Once you actually have a good way of defining your decision variables, we're talking about a decision problem here. How many of each type of car to produce? Okay? Well, in this case, of course, we have a natural definition of decision variables. I've got one decision variable for the first type of car. The second one is for the second type. So I'm going to use x1 and x2. x1 will stand for the number of Volkswagens to produce per production run. It's unknown, nevertheless. Once you assign a value to x1, it will have become known. Okay? x2 is similar, the number of Volkswagens to produce per production run. Now, when you work on homework problems, make sure you've got a good definition, a precise definition for your decision variables. If not, if you came up with the wrong definition, fine. You will not be able to express some of the things that you should like to express. Okay? In that case, you go back and try to come up with different decision variables, perhaps, to make the job easier. All right, in this case, this is natural. And then I'm going to first write down what I call the objective function for this problem. It is what you want to maximize or minimize in a given problem. In our case, of course, what do we want to maximize? We want to maximize the total profit. And if I've got x1 units of the first type of car, and if each one gives me 20,000 Turkish lira profit, of course 20,000 times x1 is your total profit coming from the first type of cars. The second one, each one gives you 10,000. So times x2 is your profit contribution coming from the second type of car. Typically, traditionally, people use a z for the level of profit. So let's just put that down. You don't have to. Nevertheless, z is the total profit you would obtain from this combination, x1, x2 combination of producing these cars. You may also scale this down, because if you're maximizing, this is a linear function, a constant times a variable plus another constant times another variable. This is a linear function, which I'm sure you are all aware of. And if you're maximizing a linear function, you can scale it down or up the way you wish, and it will not affect your optimum. If you don't agree with me, later on, I'm sure you will convince yourselves that that is the case. Okay? So when you scale down, you can surely write maximize. Let's just make the first one z prime. Let's use z for the second one. Maximize z, where z is equal to 2x1 plus 1x2. Okay? So whatever values you get for x1 and x2, the true profit will be 10,000 times what you would get from here, okay? From the scaled down version. All right, next we have constraints. The restrictions that you should obey. But for constraints, I think we have little time. So let's just take a 10-minute break at this point, and then I'll talk about the rest of the problem. Okay? Programming models in a course such as 202 here. Okay. How many people have no idea what linear programming problems are all about? Just raise your hand. Which department are you from? EE? You have no idea what linear programming is all about? A little bit. Okay. Well, you'll have to bear with me. Well, at the beginning, I'm going to give you somewhat more elementary models, but then later on, we'll start talking about a bit more advanced models, not too advanced, but something a little bit more than undergraduate level. And then there's no syllabus right now, so I'm going to distribute the syllabus by mail, as well as perhaps next time I'll give you a printout copy of the syllabus. This course will be an introductory but somewhat upper level course in linear programming. Some of you might have been already exposed to linear programming concepts from your undergraduate courses. Let me see how many people have been exposed to, for example, introductory level linear course.
I
Which one? The one taught by Bahar Kara? Okay. So you have some familiarity. What about you?
I took management science from management department in undergrad.
Who taught it?
I forgot.
I asked the wrong question. It's okay. Which are this management department here in this university? Okay. Anyway, for those of you who may not be too familiar with formulation examples, you'll just have to do some extra work at home to perhaps cover what we want to cover during the course. Now, after that, I'm going to start talking about actually solution approaches to linear programming models, because this course covers basically the geometry as well as the algebra of linear programming problems, in addition to some initial expository material on formulations. And later on, we'll start going into somewhat more specialized topics. And so, if you're not familiar, you'll have to perhaps put a little bit extra time at the beginning compared to other people, okay? Anybody from management or economics here? Did you get exposed to some linear programming material before? In the course syllabus, I don't have it with me. Nevertheless, I'm not going to give you any homeworks. That's one important component of the course. Last semester, I actually gave weekly homeworks, and then many people found it beneficial. Nevertheless, some people really complained about it. You know, this is too much work. Well, I don't really care. It's, you know, learning is your business. You learn. My business is to make it easier for you to learn the material. So if you attend the lectures, it's to your benefit, because I extract the more important stuff from the less important stuff. And so if you can learn, for example, maybe 80% of the